Cool. All right, so today we're gonna go over some just basic like LQR kind of roadmap kind of stuff, like how all these LQR and MPC ideas fit together and when we use each of them. And then I'll go over again some more linearization stuff and explain in greater detail why sometimes we can use the matrix exponential and sometimes that we can't. And I know this showed up a lot on the homework. There's tons of questions, so hopefully this will be a good time to ask questions if they come up. So let's get started. So first I'll do like the control roadmap because I feel like that's what a lot of people are a little confused on. So today is 3/17. So basically I'm going to write like a flow chart. So this flow chart is going to say linear dynamics. So this is going to be like a flow chart. It's going to be like, what do I use to control my linear system when I have certain things at play? So I'm just going to assume that I have a linear system. So I assume I have a linear system. First question is quadratic cost. So if I have a linear system and I have a quadratic cost, so I'll say yes, no, and then I'll have unconstrained. So linear system, I have a quadratic cost. If I do have a quadratic cost, and then my thing is unconstrained, then I have one of two options. So I have these are the things that we use in this case. So time varying LQR, this is us tracking a finite time trajectory. So I'll write this is tracking or any finite time trajectory. And then an infinite horizon LQR. This means that my control objective goes from now until the end of time. So I'm just trying to regulate forever. So t equals infinity. And I'll talk a little bit more in a second about kind of why we can make this assumption because we have some questions about this as well. So the next thing is, what happens if I have constraints? So now I kind of have, now I'm in like the MPC kind of realm. So this leads me to MPC. So I guess the important thing here is that if I have anything that's non-quadratic cost, I have to use MPC. If I have constraints, I have to use MPC. So all these things are going to result in me having to use MPC. So unless it magically has linear dynamics quadratic cost, I can use LQR. If not, I have to use MPC. Now I can still be convex, like the costs are still convex, it can be convex MPC. That's kind of like what we always want to shoot for. But in general, where there's no guarantee that like everything we can do, we can put into an MPC problem. We assume the cost is going to be convex. If the problem is unconstrained, we use LQR. If it's constrained or has a weird non-quadratic cost, we use MPC. So we had some questions specifically about kind of like the relationship between these two things, and it's totally valid. So I guess I'll kind of give some examples as to when we'd use one versus the other. So I'll do TV LQR. So if you remember, this cost function was minimizing over I equals 1 to n. And this is, it's good for two really good things. So the first thing we'll do is any finite trajectory, we want to use time varying LQR for, or finite horizon. So I will say this will always have finite horizon. And the second thing is that it can be time varying. And there's also like a little bit of subtlety here. So the reason that this can be time varying, that's totally fine. Time varying linear systems are fine for us. But if you can imagine, people would ask like, oh, why can't I do time varying LQR for the infinite horizon case? And if you think about it, like, how would you express this thing as a function that just varies in time forever? You know, you wouldn't have a list of A's and B's at different time steps from t equals 1 to infinity. So if it's ever time varying, it usually means that you have a specific time horizon in mind, and it means you have to use TVLQR or finite horizon LQR. So it can be time varying. Then what's something else I can say about this? That's probably sufficient. So this is time varying LQR, and then we have infinite horizon LQR. Oh, also tracking. So I can do a tracking controller if I have a trajectory that I like. So say I have a 100-step trajectory and I want to track this thing with LQR. I would use time varying LQR with the A's and B's at every individual time step. And I would track some maneuver. So a scenario where you use this is, say you had like a robot that was about to do something fancy, right? So you had like a cart pull trying to do a swing up, or like a quadruped trying to do like a jump or something. If you had a specific maneuver in mind that was finite horizoned, you could track it with TVLQR. And this is like, a lot of cool control videos are us doing these very short horizon, like cool, like athletic maneuvers kind of thing. So this is where like the finite horizon trajectories come into. The next thing is infinite horizon LQR. And if you remember, I'm talking about a cost function that goes on from now until the end of eternity. Supposed to end right here, I have infinity. And this is regulator. So I think the best example of this is like the most useful kind of control system. So like in academia, we love these like crazy control systems that make us do like really cool things. In reality, most control systems in the real world are kind of very much a set it and forget it style. So I have like a temperature control in a room or something. I just want to like regulate about some set point forever, and maybe that set point moves. But I'm not thinking about any sort of planned trajectory or finite horizons or anything. It is trying to stabilize or regulate about something. And this is when we use infinite horizon LQR. So, cruise control on a car, anything that you can think of that's not trying to do any one specific maneuver, but is more just trying to regulate forever, you'd use infinite horizon LQR. And people have some questions about why does the Riccati recursion that we use to solve for the finite horizon LQR converge to the infinite horizon LQR? And this is a super good question, and it basically comes down to the following. So if you imagine, if I told you that you had to optimize over, so say I said you wanted to do the following. You want to minimize our finite horizon term, goes 1 to 10, and I'll just put our cost right here. If I told you that you had to minimize from 1 to 10, and say I'm just doing like a non-time varying, so I have just A and B. So x k plus 1 equals ax plus bu. So say I have linear dynamics, not time varying, and say I want to solve the finite horizon LQR problem over the next 10 time steps. You can imagine I'd act a certain way. Like that first step I make is going to be like something that gets me towards whatever I want after 10 time steps. And if you imagine if I make this like 100 time steps, then my first action is going to become something else. If I make this like 1,000 time steps, I'm going to reach a point where it doesn't matter if I'm planning to do this maneuver for 1,000 time steps or 10,000 time steps. That first control move that I'm going to make ends up being the same. And so the idea is that like when I solve this Riccati recursion, what I'm doing is I'm solving for a feedback policy that I'm going to use at every time step. And in this case, if those time steps extend from now until forever, there's a certain horizon where once I exceed that, my first move is going to be the same no matter what. So whether it's 100 time steps, 1,000 time steps, a million time steps, this is specific to every problem and the DT that you're using. But you'll reach this point where the Riccati recursion is going to stabilize about some cost to go and about some K. And I'm going to have the same feedback policy no matter how much longer my horizon gets. So what we're seeing is that like as we take our finite horizon LQR problem and we make this problem longer and longer and longer, it becomes the infinite horizon LQR problem. And this is why we can use the Riccati recursion and we can keep doing it until what we see is that we'll have, this is the plot you guys made on a previous homework, but we do this Riccati recursion and then here's like our time step K. And then here I'll have, our control gain values K. And what you'll see is that, here's 1, 2, 3, up to n. So, it's like a complete normal x label. And what we saw is that these values are going to start as something, and they're all going to converge to like steady state values. So in your previous homework, you saw this kind of thing. And basically what this means is that like, if I think about this section right here, this is me computing the finite horizon LQR problem for these last certain number of time steps. Then I say, this is me solving for that certain number of time steps. There reaches a certain horizon I'm looking at where it doesn't matter how much longer I make the horizon, my first control move is always going to be the same. And that is when these things have converged. And this is why the Riccati recursion, we can use this and we can just keep iterating. And then all of a sudden we see that our K is going to stabilize and our P is going to stabilize, and they're going to converge to finite values. And then we just use those, and that is our infinite horizon LQR game. Alternatively, you can solve the Riccati equation. So when we have this function, it's like S is some function of like A, B, Q, R, S. I have like the discrete algebraic Riccati equation. So you could use this, and if you think about what the recursion actually means, it really is finding like a solution to this Riccati equation by doing the recursion. All right, so now I'm going to shift gears a little bit, and now I'm going to talk about some linearization stuff, or more linearization and the discretization, because I know that the matrix exponential stuff threw some people for a loop. So we went over the first time, so I'll talk about, okay, LTI, ODE. So LTI stands for linearly time invariant ODEs, and I'm going to assume for now that I have no control usage. So all I'm thinking of now is that I have this x dot equals AX. So I think there's like a lot of confusion about this, and it is definitely a little confusing. So I'm trying to lay out like when we use the matrix exponential, why we use it sometimes, and why we don't use it other times. So there's just one very specific case when we do use the matrix exponential, and that is when we're trying to solve ODEs for LTI uncontrolled systems. So if you imagine, if I had this right here, in this class, we've been doing a bunch of stuff where we're using all sorts of integrators like RK4 and midpoint. And then on the first homework, we used like a bunch of implicit integrators like backwards Euler and Hermite-Simpson. So we've learned about all these different integrators. And so if I gave you an ODE and I said integrate this, you could use any of those integrators and that would be fine. And what you're doing there is you're numerically solving the differential equation. So you are using numerical integration to solve this thing, which is oftentimes like the best that you can get, but in the very specific case of LTI ODEs, so anything that looks like this, I can solve this thing exactly. I can integrate it perfectly without using any sort of numerical integrator. And this was from the following. I could do x of t equals e at x of 0. And this is our initial condition. So if you remember this, I can solve for what x is at any point in time by using this matrix exponential, or the state transition matrix as it's called sometimes, times my initial condition. And so I'll just draw this out kind of graphically as to what's going on here. So if you imagine here's t, here's x of t. So what I can say is, and so I'll have this be like x of 0. T equals 0, x 0 right here. And what I'm saying is that at every single one of these points, the slope of this is AX. And then what I can do is that by doing this right here, I can solve for the exact value of what this thing is. So this is me solving this differential equation exactly. I don't have to use a numerical integrator. If I have a linear system, I can integrate it exactly and perfectly just by using the matrix exponential. And this is the one and only time in which we'll do this. And so a more kind of control-Z, I guess, look at this is normally we don't want to integrate from here until forever. We're really looking at these time steps. So I want to do this whole, x at time step k plus 1 equals e a dt x k. So this is a totally equivalent and acceptable way to write this right here, but we just happen to write it in terms of this dt. And this makes everything much like more straightforward. We're talking about like a dynamic system that's like evolving in a discrete fashion. So what we've done here is that we've used the matrix exponential to discretize this LTI ODE. So we started out with this, the ODE, and then we used the matrix exponential, and we got this right here. And oftentimes you'll see this thing called AD. And this is our kind of discrete time A. This goes by a lot of names. And oftentimes in the class, like Zach and I we'll just say A, because we'll assume we're talking about discrete time. The second thing comes when what happens when we have any sort of control input. So control inputs are totally fine. Turns out I can just do, if I have this, if I have x dot equals ax plus bu, so I'll call this section first order hold on u. So assume I have x dot equals ax plus bu. This is still a linear system. Everything about this is still good. Turns out we can still integrate this exactly, but we have to understand how u is changing. And this is a decision that kind of comes up to the engineer. So what we have is, if you imagine how I want to control this system in terms of the actual logistics of like how I send my control inputs, is I'll do the following. So here I have u, here I have t. So what is most common, and I'd argue is most practical for dealing with control, is doing a zero order hold. What this means is that at every time step, I have a new control, and I just hold that control steady for the entire time step. So this is zero order hold. And what this means is I'm maintaining the zeroth derivative. So I'm just maintaining the value between t and t plus 1. And remember that this is the distance between these things is dt. So our time step size, I'm just holding u constant. And the reason I think this makes a little more sense and is a little more practical is because if you imagine when I control a robot, say I'm controlling a quadruped, at every time step, I will command new motor torques, or a quadrotor. I'll command a new value every time step, and then do my control estimation stuff, and then update the control every time step. And when I update this control, I'm setting it to a new value, and I'm not like setting this thing in a derivative. So I don't say like to this motor, like, okay, here's a torque value, use it, but then increase it linearly at this rate. That would be a first order hold. And we'll talk about that in just a second. So if I assume I have a zero order hold on u, now let's talk about how we can integrate. So I want to integrate from k to k plus 1. And so now there's like a slight nuance here. So if I'm integrating from time step k to k plus 1, and again, I'm integrating dt, so a small amount of time forward. And if I think about this zero order hold, what I'm doing is I want to integrate from this point right up until this point. So right up until it changes. And I'm going to assume that this u is going to be constant the entire time. And so how do I write down the ODE for this? Well, I say that between k and k plus 1, u is not changing, right? This is a zero order hold. U is constant throughout that whole time step. That means u dot equals 0. So now what I can do is I can define kind of a new state, and I can look at this ODE again. I can look at this right here, and I can write it down in a way such that we can use the matrix exponential once more. So what I can do is I can say x u, I'll call this new state like x tilde in a sec. A, B, 0, 0. Okay, so now what I've written down right here, this is the exact same as this, right? I just stacked x and u up, and I said this differential equation I just wrote down is an exact restatement of this right here. The benefit is that when I write it down like this, I see that this is kind of in the same form as I had before. This is kind of, I'll say x tilde. So I'll say this is like some new state x. This is, sorry, x dot. So once again, I have this thing in a LTI looking ODE. So I have x dot equals ax, where my x is now defined as a concatenation of x and u. So I have this, and this means that I can now solve this thing exactly. So I can do all the usual stuff. I can say x k plus 1 u k plus 1. And then what this starts to look like is this thing will end up having this structure. It'll look like this after we take the matrix exponential of this a tilde times dt, we're gonna get this. And then what we get is that we all care about is the top equation. The bottom equation tells us nothing. This just says that u of k plus 1 equals identity times uk. So uk plus 1 equals uk, because remember, we're holding it constant throughout that whole time step. And so when we take this matrix exponential, what we get is that we get ax k plus 1 equals ad xk plus bd uk. And this is how we just discretized a linear system using the matrix exponential. So hopefully these two examples I just wrote down are pretty straightforward, but this is all you have to know about when you should use the matrix exponential. If you're not doing one of these two things, you don't need to use it. So in question 2 of the homework in part A, we said, hey, here's a cart pole. It's currently sitting upright. Linearize about the system and design an LQR controller for it. And we had some people kind of do some weird stuff where they were using the matrix exponential, which is it ended up working. It was incorrect, but it worked for part A. But it should not have worked for part B, or for most people, it did not work for part B. And that's because the only time we should use this is when we're discretizing a linear system. And this is not that big of a deal because we can form derivatives of everything we want to pretty inexpensively. And actually taking this matrix exponential is super expensive, because if you remember, what this actually looks like is this is a power series. So basically I have like this big power series here. And this is like really expensive to compute. And when I call this in, SciPy or MATLAB or whatever, when I call this thing, it's going to go through and it's going to do like a bunch of clever numerical methods to try and compute this infinite series without actually computing all the infinite terms. But it still ends up being like relatively expensive. Okay, so I got a question. How do we know that E a tilde dt is of that form? So this comes down to, how do I know that E of a b 0 0 dt equals I plus AB 0 0 dt plus AB 0 0 squared dt squared over 2. So if you need convincing, you should just try this in Julia or MATLAB or whatever and just see the structure it takes. But basically, when I add this I, this is how I get the I down here. I kind of add an I to this, I to this. And then as I kind of do this thing forever, what you see is that it's always going to maintain this structure where this will always equal. It's going to have a dense block here, dense block there, all zeros here, identity matrix here. So it'll always look like this. Why do we even think the matrix exponential is more expensive than the alternative? Okay, so the reason that we use this at all is because oftentimes we have a linear system. I know what it is, and I just compute it offline once, and I'm good forever. So for instance, like with the double integrator that Zach talks about in class, that this is a classically studied system. I can take, if I have a linear system of a linear model of my system, and I'm like confident this thing is a linear system, I compute this matrix exponential once. This gives me my discrete time AD, BD, and then I never have to worry about it again. So this is not a value that I should ever compute online. This is a value you compute offline. So it doesn't really matter how long it takes. It could take like, an hour to solve for it and still be super useful, right? Because I just solve for it once. And now I have this like clever way to exactly integrate linear systems. And I use this for all my control work and everything's totally fine. But you should never, you should never compute this thing online. This is totally like an offline tool. These are super good questions because these are like not obvious until you like go out and try a lot of things and like think hard about why you should and shouldn't do certain things. How does this discretization even work? how does equation work at the discontinuous? Okay. So yeah, this is a little nuanced. So basically what I think what I was trying to get at is how does this thing kind of work? Because we have this like discontinuity for the zero order hold between time steps. So we talked about here is that this integration that I'm doing, it's just from here up until like infinitesimally before the control changes. So with the zero order hold, I'm saying that U is going to be constant the entire time. At the next time step, U could be constant the entire time. And the reason this is totally acceptable is because if I look at this differential equation I wrote down right here, this is not just true between this time step and this time step, right? This is true everywhere. So whether I'm integrating between here or here or here, it doesn't matter which dt between time step k and k+1 that I'm integrating between, u dot will always be 0. So this differential equation is totally fine. And the one thing that we like take into account is that if you remember, for just a generic linear system that is just x dot equals ax, I had this like initial condition. And this is kind of how I bake in the information about like where is the system currently at. And this is the same thing here when I compute this with xk uk. So everything about this ODE that I wrote down is true for a zero order hold. This is true between any time step I have right here. And then the way that I kind of bake in the information of like, well, how does this system, when I integrate it, how does it know what the current value of U is? This just comes from this right here. My initial condition tells the system during integration what the current value of U is, and that's how the solution is correct. And you guys should definitely, like, I think a fun exercise that maybe I'll put on a homework is comparing like RK4 integration to this, and you'll see that like you can basically integrate this thing perfectly just by using, matrix multiplication, which is why this thing is so valuable and why we can just compute this exponential once offline and then online save ourselves all the trouble of RK4. Not that it's that much trouble, but obviously if we can get away with just doing matrix multiplications, we should just do that. Does that answer your question?
Kevin,
Yeah.
can you hear me?
Mhm.
Yeah, if you don't look at the graph of U and you just look at the equations that you've written, it would seem that UK is constant forever.
Yeah. So if you see, I cleverly, I only pulled out the top equation from this thing. The bottom equation says the following. The bottom equation says UK plus 1 equals UK, right? So you kind of wonder like, I set this thing up here. This gives me two equations. I just grabbed the top one and like threw away the bottom one. And the reason why I did that is because this model, by saying U dot equals 0, I'm assuming that U is the same throughout the whole time step. So I assume that UK plus 1 equals UK because, in theory, this thing is discontinuous. So it has a value at both these points, right? So it's true that UK is the same as UK plus 1, kind of, like, because this thing is discontinuous. But it's true when we integrate that between this time step, between here and here, we just assume that UK is constant. And that means that U at the end of the time step is the same at U at the beginning of the time step. And so because I wrote down U dot equals 0, this
So,
second equation
Kevin,
doesn't tell me anything I don't know.
yeah, I'm thinking in terms of the integrator, like RK4. So at every time step, do we have to uh, intervene and give a new value of U that we have used?
Yeah, so if you imagine like RK4, um, RK4 tells me this. And then I'll just real quick. So one thing that's super useful to note about RK4 is that notice how U is the same everywhere.
Got it. I think my doubt's clear.
Okay, cool. I'm just gonna finish it because I started. So when I use RK4 to integrate a generic ODE F, so say I have this x dot equals f xu, and this is a zero order hold. So if I assume a zero order hold for this thing, when I integrate with RK4, I hold my u constant every time step. Because if you remember, this thing is being computed at this is t equals 0. This is at the midpoint. This is at the midpoint. And this is at dt. So here's kind of like where these, the way RK4 works is that these function calls all happen at different times. And I'm like using this to cleverly approximate to third order what my solution is. And I'm approximating as a third order spline. And so for a zero order hold, that means u is the same throughout the whole time step. So u is going to be the same for each of these function calls. All right, so now I'm going to go through some linearization stuff. So this is very specific to problem 2. I had like this linearization warm-up stuff that I wrote at the top of the question that didn't quite seem to answer it for everybody. So what I'll do is I'll kind of spell out like why we just diff through the discrete time dynamics and why we don't want to use like hammer it again, like why we don't use the matrix exponential anywhere. So I've written this a few times, but also I'll go relatively quickly. So if I have a discrete time model, this. Ooh. So this is my discrete time model. I can linearize this system with a first order Taylor series, and this gives me the following. Xk plus 1 is approximately. So I will do linearize at x bar k, u bar k. So let me actually make this a little more clear. Xk plus 1 equals f xk uk, which is approximated by the following first order Taylor series, plus df du at x bar k, u bar k, and then uk minus u bar k. So here I'm saying that I have this discrete time dynamics function. I make no assumptions about its linearity. What I'm saying is that I want to linearize this thing by taking the first order Taylor series of this. So I take my f of xk uk, I linearize about an x bar u bar, and this is just, go on Wikipedia and search about like a first order Taylor series. This is what it is for a function with two variables. So I have the current value at this point, and then I have this Jacobian evaluated at the linearization point times kind of our delta and this. So this is like how we linearize the system. And what we use oftentimes in controls is we'll say that x just generically is this, and u generically. And if I do that, and if I make these substitutions into the above system, I get the following. So we'll just copy this, paste it down here. And what we'll do is we'll just take this out, and just by substituting, this gives me delta x, delta uk. And then opposed to xk plus 1 here, I'll say this is does that make sense? So oftentimes what we have is that we are going to linearize about a dynamically feasible trajectory. So I'm just going to write down like this is true. So if you hear dynamically feasible, this means that x k plus 1. So if it's dynamically feasible, so if x bar u bar dynamically feasible, it just means that when I plug it into the dynamics, that this is actually true. So if I apply these u's, it means I get these x's. So dynamically feasible just means that like this constraint, if you will, is satisfied. And so what does that mean for this right here? So let's do some quick notation stuff. So this, I'll call this just my A matrix, A of K. And this, I'll call my B matrix, B of K. Now, if I say that it's dynamically feasible, that means that this is equal to this, right? This is what I said right here. Dynamically feasible is for my x bar and u bar to be dynamically feasible. F of x bar u bar equals x bar k plus 1. Now, if these two things are equal, then I can just remove them both. So I'll do, remove this, and now I get the following. I get delta xk plus 1 and there I have linearized the system. So what this required was this required me forming these Jacobians. So what these Jacobians were is that these Jacobians are the derivatives through my integrator. So when I have xk plus 1 equals f of xk uk, I remember I made no assumptions about the linearity of this thing. I could assume this thing could be RK4 or midpoint or whatever. And I form these Jacobians by differentiating through this integrator. So I have integrator plus dynamics, and it's integrating from time step k to k plus 1. And these Jacobians, I diff through that. So I'll write again up here. So this could use RK4, Euler, midpoint, etc. And then I'll just point you to homework 1. Q1 is where we played around with all these integrators. So I had this discrete time dynamics model. I assume I'm just going to use, I'm using some integrator, some explicit integrator here. So RK4, Euler, midpoint are all explicit integrators. And I'm using this to propagate my state and control at UK to xk plus 1. And then what I said is that I just followed this super simple process where I formed the first order Taylor series. And I said, you know what, let's define these deltas, which could potentially make our lives easier. And it turns out that if x bar and u bar are dynamically feasible, aka they satisfy the dynamics, like xk plus 1 actually came from xk uk, then I can just remove these two terms and I call this ak bk. And now I have this thing right here. And this looks just like a linear system, but in terms of x's and u's, I have delta x's and delta u's. And so what I did is I took a nonlinear system and I linearized it by differentiating through my explicit dynamics function, sorry, my discrete time dynamics function. And so what people were doing, which is incorrect for question 2, part A, is people were linearizing the system in the continuous time dynamics. So they're forming like a delta x dot equals a delta. So yeah, I'll write down what people were doing. So people were doing the following. So alternatively, if I had x dot equals f xu, I can linearize this system the same way I did before. I can now say that x bar dot, which is not changing. Actually, I'll write down both things. So I'll say x dot equals f x u k approximated So actually, I'm going to make a distinction here so this is not confusing. I'm going to call this thing D. This is my discrete time dynamics. I don't want to overuse F to confuse people. D, 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 D. So I called my discrete time dynamics function f of D. And now I have an ODE. So this is not a discrete time system. This is my ODE. And I can, again, this is just a function with two inputs. I can take a first order Taylor series of this, the same as I could the discrete function. And I can linearize the ODE right here. And again, I can just do the deltas. I can do x equals x bar plus delta x. U equals u bar plus delta u. And what I see is I get this x bar dot plus delta x dot. And this is going to be 0, right? Because my x bar is not changing. Just assume that this linearization point is just fixed. And that doesn't mean that this linearization point is a fixed point. It just means that like I'm not changing my definition of what x bar is. X bar is just some value. This equals, and then I'll call this, let me go back here, AKBK. Okay, that's fine. I'll call this like, just to not abuse it, this will call this A bar and B bar. So what people were doing is they were taking this system, one last thing. Again, if I assume this is a fixed point, so if I assume that the dot come out of this thing is 0, that means the x bar u bar is an equilibrium point. So with the cart pole is swinging up, and I linearized about this point where it is like, you know, if I perturb this a little bit, it'll go unstable, it'll go away from the equilibrium. But if it's sitting there perfectly up top, it'll stay right there. So when I plugged in, this is a control of 0 and a state of x equals 0 and pi, or theta equals pi. The cart pole is just standing upright. If I plug in that state and control, I get out no change. My derivatives are flat. That means that my system is not changing whatsoever. It's stable up there, right? In a very scary sense. So this thing is going to be 0. So what I get is I get delta x dot equals a bar delta x plus b bar delta u. So here's what people were doing. People were linearizing this system in the continuous time sense. So they're doing this page right here. They were linearizing the system. They were forming this right here. And then they're like, oh, look, this is a linear system. The same way it was the very first thing we went over when we said that x dot equals ax plus bu, and I can integrate this thing exactly using the matrix exponential. They were forming this and like, oh, sweet. And then they were taking the exponential. And the reason that this worked for the first problem is because the state is not changing. So while this is still incorrect and super slow to do, you can get away with it in the case where I'm just tracking an equilibrium point. And that's because in the time step, it's not changing. And so let me kind of spell this out. So if I'm at some equilibrium x eq u eq, what I'm saying is that the derivative is 0. So, you know, for the cart pole, I'm up here, the derivative is 0. That means that from the time step perspective, if I look at, you know, t plus 1, here's x. This means that x is flat. So x is not changing in time. And what we talked about is that in order to integrate this thing with a matrix exponential, this linear system has to be linearly time invariant. So it does not change in time. So this is why, even though this is incorrect and unnecessary, you could get away with this method for question 2, part A, but you couldn't for part B. And I'll explain that in just a sec. I guess first, before I move on to that explanation, does it generally make sense as to why these two things are different? How in this case, I linearized my discrete time dynamics by taking these Jacobians through my discrete time dynamics function. And this, with like modern auto-diffing tools, is totally doable and easy and fast. And then this is, I kind of did a similar process, but I just linearized about the continuous time dynamics. And this is not something we're going to use in this class. Like if you're doing this for some reason in the class, like you should be super, like basically make sure you're doing the right thing, because it's very rare that we're going to do this in this class. We like to think about everything in terms of discrete time systems because we control things with computers and we solve everything in a discretized version. So we love solving discrete time systems in this class. I'm just like letting you know that this is something you can do. You can linearize continuous time dynamics, and like a lot of controls classes do stuff like this, but it's not advantageous to do so. So forming this and then taking the matrix exponential is not helpful. It's slower than doing what we did on the first page. So now I'm going to talk about why this didn't work for question 2, part B. So question 2, part B, this was a trajectory tracking problem. So I had, if you remember, I was tracking an X and a U. So I had a carport that was doing a swing up, and I wanted to solve for when this thing swung all the way up. And then if you imagine, if I were to take this system right here and I were to linearize it. So if I were to take some point right here, some point right here, and make this my X bar, and I linearize about that time step in the function, if I form the discrete time approximation, what I'm doing is I'm kind of considering all the data from time step t plus 1. And so let's write out the following. So say I have an X bar and a U bar, and this is what I just drew in blue right here. Say I have this, I'll just do X bar, U bar. I could form the continuous time Jacobians. So I could do d of x dot d of x. Forming these continuous time Jacobians gives me the information of this function at this point. And then using the matrix exponential assumes that this behavior in this linearization is the same for the whole time step, which is not the case. Now, alternatively, if I were to take dxk plus 1 dx and dxk plus 1 du. Now I'm considering like more of the time step. Does that make sense? So basically what we're doing is that we're comparing the following. We are comparing, actually, I'll do this for a one-dimensional system, and I think it'll make a lot more sense. So say I have x dot equals f of x, and I have some linearization point, this right here. The two things that we kind of compare doing is, the first is matrix exponential of df dx dot times df dx at x bar times dt. So we're comparing taking the matrix exponential of this Jacobian, or, so this is the bad way. And the good way would be to just take the discrete time system. So take this xk plus 1, discretize it with an integrator. Discretize this, xk plus 1 equals fd of xk. And then now what I'm going to do is again, still linearizing about this point xk. And then now what I'm doing is I'm saying that dfd So do you see how kind of these things are different? So I can first linearize and then discretize, or I can discretize and then linearize. And we basically want to discretize first. So I know this may not be looking super clear now. So do you guys have some questions about kind of how these things are different and why we do one but not the other? So let's look at, I think of a good example of why this is different. I guess it comes down to the fact that like this system is moving. So when I take actually I have a much better example. I'm going to pull up some RK4 Jacobians. Okay. I'm going to stop this share momentarily. Okay, so what I have here is this is a function that helps me compute my RK4 Jacobians given a continuous time dynamics function. So here's RK4 step Jacobians, and what this does is I just wrote down some function, dynamics and Jacobians, and this is going to return an x dot, and it's going to return a continuous time a and b. So just for some context, so here's dynamics, make this a little bigger. I have my dynamics function. I have just Euler's equation with some random nonlinearity thrown in there. Then I have my integrator. I use RK4 for this. And then my dynamics Jacobians is I just take my A and B are dynamics this, dynamics this. So these are my continuous time Jacobians. And then I have this function that I call dynamics and Jacobians. And this is where I take in an X and a U. And I'm going to return X dot, which is the dynamics or the ODE at X and U. And then I'm going to return the continuous time Jacobians A and B. And so what we do is that when I talked about how the best thing for us to do is we want to diff through the integrator, I want to form this Jacobian A. So I want to get the Jacobians of the discrete time dynamics as I push it through RK4. And as Zach has said, we can do this with modern auto diffing tools, and this is super fast. And if you look at, here's how we can compute this derivative kind of analytically as a function of the continuous time Jacobians. And what we see is the following. So here's RK4 step Jacobians. This is going to take in an x u dt. It's going to give me the state at the next time step. And it's also going to give me the Jacobians if I were to diff through the RK4 with the dynamics function. And so at each of these function calls, I have, remember, with RK4, I compute this value at 4 different points. So here's at the beginning point, and then these two are at the midpoint, and this one is at the end point. And all 4 of these are computed at different values of x, but since we have a 0 order hold on u, it's the same value of u. So what I get is I get 4 x dots, and I get 4 a's and 4 b's. And when I compute my AD and BD, and these are my discrete time Jacobians, you can see that I'm incorporating information from all these a's, right? A1 through 4 are all used. So these are continuous time Jacobians of this function at 4 different values of x. And all this information, this is between xk and xk plus 1. The derivatives of this function at 4 different points between xk and xk plus 1 is considered when I form my discrete time Jacobian. And the same thing for b. For b, I have all 4 of the b's show up, as well as all 4 of the a's show up. So when I form these discrete time Jacobians, I'm incorporating information about everything about the state at 4 different points for RK4 between time step k and k plus 1, and that's how I get my AD and BD, or my discrete time Jacobians. Now, alternatively, if I were to do the linearize first and then discretize, I linearize at xk, and I only get information about those derivatives at xk, and then I use the exponential to discretize. So I'm like ignoring the time varying nature of the solution to this system, and that's what makes these derivatives for part B wrong, because I need to incorporate all the derivative information that happens at these 4 points. I can't just take the first point and then just take, the exponential of these A and B right here and just propagate that forward, because x is changing. And that means that the derivatives of this thing are going to change throughout the time step. So I can post this up on the Recitations repo. I think it's probably like a nice resource to look at. It kind of shows how these things are the same. So you can see like here's like normal RK4, and I did the RK4 step Jacobians, and I computed the difference between the analytical Jacobians for the discrete time system and the forward diff ones. And we see that these things are, 0 in floating point precision. Does that like help make this thing a little more clear as to basically why taking the discrete time Jacobians incorporates more information about the progression of this system than just linearizing at one point and then just like exponentiating? All right, cool. So that's all I have planned today. So if you guys have questions, I know we just had a homework due, so maybe not as many questions as normal, but I'd be happy to answer anything that's going on right now. All right, if not, I will see you guys next week.